I work for a French consultancy called Libre, and today I'm going to be talking about GPIO user space. We are a small French consultancy based next to Nice. We are around 20 people now. We are involved in the whole embedded Linux or embedded systems stack from low-level firmware to bootloaders, the Linux kernel, up to the user space and build systems. We work on both software and hardware products. We contribute significantly to upstream open source projects. And we are the founding developers of the kernel CI project. So how many of you have already played with GPIOs in Linux? So, the vast majority. So you are probably familiar with the concept. So GPIO stands for General Purpose Input Output, and it's probably the simplest way of interacting with hardware. So it's basically a generic thing that can be configured at runtime. We can either work in input mode where we read values that someone else is driving, or we can work in output mode when we drive the thing. Then the GPIO can have, it can take a binary value, so it's either high or low, or enabled, disabled, whatever you like, and then you can use it. GPIOs can also be configured in input mode to be source of interrupt for the system. So it's quite simple, but it has a number of applications. So whenever you need these whenever you have these binary values to use, you can. It's good to use GPIO. So when you have buttons, when you have LEDs, buzzers, power switches, stepper motors, or LED detectors, all these devices that basically are enabled or disabled can be driven or can drive the GPIO so that you can interact with them. And we have this concept of GPIO providers and consumers. So when these devices are the consumers of GPIOs, we have SoCs or expanders that provide GPIO. So most SoCs provide a number of GPIO lines, but since you don't want to waste precious SoC pins on simple GPIOs, you use expanders that are connected over I2C or SPI. And this model of a provider and a consumer is reflected in the kernel. So in the kernel we have currently two frameworks for GPIOs. One is a legacy framework that is deprecated, which uses a continuous GPIO number space, where every GPIO line has a unique number assigned in the kernel. And this GPIO is no longer accepted. So if you want to write a driver that uses GPIO, you need to use a new framework, which more recent framework, which allows you to assign GPIO lines to devices, and then in your drivers you can get access to them and use them. Which also allows you this new framework allows you to have more fine-grained control over GPIO lines. And both these frameworks support device resource management. The drivers for GPIO chips live in drivers/GPIO directly in the kernel source, while the consumers are everywhere because many devices rely on GPIOs. So usually what you should do is you should write drivers that change, like you use the GPIO lines, but in some applications it's actually preferred to do it from user space. So whenever there is a framework missing in the kernel, so you don't have the possibility of writing a driver, you want to drive GPIOs from user space. So for power switches and relays. Then you have devices like GPS and Bluetooth devices are a good example, which communicate over serial ports, but they use GPIOs for signaling. And then certain users seem to prefer playing with GPIOs from user space. This is, I've noticed that a lot of intelligent home systems are implemented in user space, and also robotics, which often uses Python and plays with GPIOs from user space. And up to recent under the version 4.8 of the kernel, the standard way to interact with GPIOs from user space was the sys class GPIO interface. How many of you have used it? Yeah, so this interface has been merged in the following comic. This was during the time where the GPIO subsystem and the kernel had no active maintainer, and someone just sent it to retro apartment and it got merged. But this interface is pretty badly designed, that it has many shortcomings. So first of all, it's a global state. It's a set of directories and files in SysFS. The state of GPIOs is not tied to any process, so anyone can just come and export them, unexport them, change values, change directions, which is not the preferred approach. Then if your process that is currently using GPIOs, for example, crashes, the state is left as it was, so all the GPIOs remain exported, the values remain set to so this is it. And then the API itself, the sys or API, should I say, SysFS is quite difficult to use, so you have multiple files for every GPIO line that you need to open and write to. The performance is pretty bad because you need to deal with string parsing in the kernel. Then the problem with this system, with this interface, is that basically the SysFS interface is a user of the legacy GPIO API in the kernel, so it uses the single number space. So as a user from user space, you need to actually know the numbers that are that correspond with GPIO lines, and these numbers not necessarily are constant, because if you have a GPIO expander that you connect dynamically over I2C or USB, these numbers will be dynamically assigned. So then the big problem is that you try to reflect a two-level hierarchy where you have the chip level and the line level in a single number space. You actually can poll for events, but it's quite difficult in that and not very reliable. So you can actually poll the value file in this class GPIO for events, and when you get a poll event, you need to else seek or reopen the file, and then you can read the value. But these events are not queued, so if your processing is slower than necessary, then you will start missing these events. So in kernel 4.8, we have introduced a new interface for GPIOs. So now every GPIO chip registers a device file in there. The device files are called GPIO chip 0, 1, and so on. And these device files can be accessed and manipulated with standard Linux interfaces, with standard Linux system calls, so open, IOCPL, call, read, close. Now, unlike the SysFS interface, you can request multiple lines at once, and you can work on sets of lines. It's possible to look up lines and chips by name, and for the record, in SysFS, it was possible as well, but it's not very well documented, and actually not very instinctive, because you have to export the line through SysFS, and if it's got a name assigned in, for example, in device tree, instead of GPIO, if you export line 1 to 3, normally it should pop up as GPIO 1 to 3, but if it has a name assigned, it's going to show up as the name, so the file is going to be called the name. But in this new interface, it's much easier. You can actually look up lines by name, same thing with chips. And then you can affect the way that the lines are driven by the kernel, so by specifying flags like open source, open drain. You can use consumer strings, so you can actually tell the kernel or the subsequent user that might be interested in it who's using the line, because with the previous interface, it's always like the consumer is always called sysfs. Now you can say exactly what your name is and then who's the user of every line. Then now we actually get new events, so we can react to new chips popping up. We can change their permissions and so on. And we have reliable calling. So now we actually call a device file, like a file descriptor corresponding with the device file, and these events can be read with the read system code, so they are actually queued in the kernel buffer. And this new user API lives in a header include UAPI and GPIO.h, and the header is logically split into several sections. So you deal with chip information, line information, then requesting lines for values and reading and setting them. You get line requests. You can separately request lines for reading the events, and then you can call these events and read them. I'm going to go through a couple examples of how to use C code from user space to manipulate GPIOs. So the first important structure is the GPIO chip info, which contains the name, label, and number of lines of the GPIO chip. And this is quite straightforward. So you just open it, open the device file for reading and writing, and you write and you call the ISPL that fills the structure with all the information. You can then print the name, label, and the number of lines. And then once you have the file descriptor for a chip, you can use it to get information about every line. In this case, you have to call the line for ISPL for every line. Analogously to the chip info structure, you have the name, the consumer, and then the offset of the line and certain, the offset of the flags that are filled by the kernel, and the line offset field is the only one that you have to set before calling the ISPL to actually tell the kernel which line you want to get info about. And for the file descriptor in this case, we're using the one that we got returned by open on the previous slide. So this is a bit more complicated. This is when we request a set of lines for setting or reading values. So we have a structure, and what you do is you specify in the flags variable the kind of or the mode in which you want to work. So you have to specify either input or output, or if these flags are not set, it's going to be considered as is, so depending on how the line was set previously. And then you can add additional flags, so you can tell the kernel that this line is going to be active low, so we are going to invert the values. And then, as I mentioned, you can specify the open drain open source flags to tell the kernel how to write the lines if it's the output mode. Once you have the flags figured out, you need to tell the kernel how many lines are there. So how many lines are there, and then there is a array of line offsets up to 64 lines can be specified in a single request. And one by one you specify the offset of the lines that you want to request, and then there are the default values if it's output mode, or you just omit this structure if it's input mode. And then the mentioned consumer label. So this is where you tell the kernel who the consumer from the user space is, and this is going to show up in the line info. Once if you would run the line info again on this, we only requested line on this, and the consumer label is going to be this string. And then again you run the ISPL on the file descriptor returned by the initial open. And then as you can see, there is this FD integer in the structure is going to be filled by the kernel with a new file descriptor that corresponds with the set of lines that you just requested. So once you have this new file descriptor, you can start copying the values of GPIOs or read them. So for that, we have another two IOSPLs to the setline values and getLine values. And this is pretty straightforward. It's just an array of 8 integers. And you just, in order to set values, you just set each field to the appropriate value. Every index in the array corresponds with the offset that you requested in the previous system call, the previous IOSPL. And it's pretty similar for reading the values, where you call the IOSPL and then the kernel fills the data structure with current values. And then another possibility is requesting the event. So this is done separately in a different IOSPL. Works pretty similarly, except that you cannot request multiple lines at once for reading events. So in this case, you have to do it one by one, unless you're using the user space library, about which I'm going to talk in a couple minutes. So yeah, the flags are the same as for requesting values, but in this case you need to additionally specify the event flags, which is just the type of events that you're going to wait for. So either rising edge or falling edge of code. Yeah, once you have set this structure, you just run your IOSPL. And again, the file descriptor is set by the kernel. And once you have it, you can start calling for events, which is pretty straightforward, just a regular call for incoming events. And once you get, once your call function returns an event pending, you can just read it. And when you read it, you get to read it into a buffer corresponding with the GPIO event data structure, which then gives you the timestamp of the event and the ID. So ID is just telling you whether it was a rising edge event or falling edge event. And yeah, so all this is, it looks pretty complicated, and the main problem with this API, although it's better and more powerful and more robust than SysFS, is that not many people want to use it because you still have to write C code, low-level C code, and deal with IOSPLs. And so my first contact with this GPIO hardware device was when we at the Libre have these Acme tapes, which are like extension tapes for BeagleBone Black that allow to measure power consumption of external devices. And we have these probes that, apart from measuring the power, also have power switches in that you can cut off and restore power to measure devices. And these probes, these power switches were controlled with GPIOs from the BeagleBone Black. And I noticed that the SysFS interface is not very useful, and I tried to implement it in the kernel. So first I sent some patches to the IIO framework. But this was shut down because these GPIOs were not really associated with any device and had nothing to do with the industrial input-output framework itself. Then I sent another try was to use the regulators and control them from user space. It was shut down as well because apparently it's a good idea. And in the end, I noticed that there is this GPIO hardware device framework, and I decided to use it. But yeah, this was pretty complicated and just not very efficient, like writing this kind of C code. And I decided to make it easier. And I wrote this libgpiod project, which consists of a C library that wraps all these IOTools with a more robust API and a set of tools. So this was written like in a span of 2 weeks and released in January 2017. The current stable version is 0.3.2, but I noticed pretty fast that this initial API for the library was had certain shortcomings. So I started to rework it. And actually, I'm pretty like next week I'll probably release the 1.0 version of the project, which has a reworked API, in which, for example, we can now request multiple lines for events and do and use a unified interface to do many operations, which basically makes the code much more compact. Also, I posted on the Linux GPIO mailing list that a request for reviews of this API. If anyone is interested, please take a look and post your remarks to the list. It would be grateful. So, what are the current features? So we have a C API which is fully documented in Oxygen. We have a set of command line tools that allow to easily interact with GPIOs from user space and can be used in scripts, for example. So this is the thing that I think is the most important. So this can actually replace using the SysFS in scripts by using these command line tools. They were a bit inspired by iSQL, so the names might make me sound familiar. And then we have a custom test suite. So this is interesting because there is this GPIO, actually it's not called GPIO, but GPIO mockup kernel module, which is a GPIO chip simulator in the kernel. And together with something called Fixing, which is an interrupt simulator, we managed to create a testing suite for both for libgpiod, for the user space part, and for the kernel part, for the kernel user space API. I was thinking initially to use some available C testing, unit testing framework, but it turned out that it was actually not very not possible because we need to work with the kernel module, we need to load it, unload it, then we need to wait for unit events to be able to detect the devices that show up, and yes, so the test is custom, but. It can be, I run it in every kernel release to just check if there are no regressions in the user API. And the C API can be split into a couple of logical parts. So there is this simple API which actually has changed the name, the name of which has been changed to contextless because apparently simple is not a very descriptive name. And then we have chip operations, line operations, which corresponds with the kernel user API. The line operations are further split into line information requests and events. And then we have something that doesn't exist in the kernel API, which is iterators, which allow you to iterate over chips and lines associated with chips, and so on. So I don't want to go much into detail about the C API. These are a couple examples of how the libgpiod code looks like. The names of these functions have changed in current Git master too, so they are no longer the same. But yeah, the idea is the same. So you do a chip open, and you can not only open the device file by path, but you can look up the chip by its label, by name. There are functions provided for that. Then you do a get line, which gives you the line info, and you can use a couple accessors on that to get the regular information, so the consumer and label. And yeah, you can easily call for events without using the system call, so you can use provided filters for that. And yeah, but the more interesting part for most people are the tools. So there are 6 tools available currently. The first one is GPIO Detect, which allows you to list all the chips that are present in your system, which lists the name, the label, and the number of lines of each chip. GPIO info goes a bit more into detail about a single chip or multiple chips, and that it lists all the lines with their offsets for each chip, and then if the lines are named, the names will be printed, and then the current direction and user and some other flags will be shown. And then we come to the GPIO find. This is a tool that allows you to look up lines by name. The usage is very simple to just run GPIO find and the name of the line, and then it gives you the name of the chip with which this line is associated and its offset. And actually the output of this tool can be used together with GPIO get and GPIO set commands, like it's shown on the slide. So now we pass the output of this GPIO find tool to GPIO get, which reads the value of this specific line. Next, we have the GPIO set tool. So one interesting thing about this character device is that if GPIO lines are driven high or low by default in the system, once you close, unlike a floating pin, once you close the character device, it's going to return to the default value. So this is not the case for sysfs, because as long as the line is exported in sysfs, even if your application is no longer running, the line is driven, right? You wrote the value, so it's driven. So with GPIO set, you can simply set the values and exit, but you can also specify several modes, additional modes. So in this case, in this example, we're using the wait mode, which waits for user input. You can specify timeout mode, so you can set the value for 2 seconds, for example, and then exit. You can wait for signals, and there are a couple more modes implemented. And then the GPIO mon tool allows you to monitor line events. In this case, you can specify either one or more lines associated with a GPIO chip, and then GPIO mon will print the events as soon as they arrive. Actually, it should be on a single line, but and then if you want to parse these events in scripts or in programs, it might be useful to use a specific format, and it's documented in the README. You can specify your custom format of how the events should be printed like. Which is useful when you don't want a really string. So this is the current state of the project, and there are some certain things that I still plan and want to implement. So I almost finished writing object-oriented C++ binding for the library, and this is done because the C++ 11 standard allows you to do this kind of manipulation in a much more straightforward way because of the new features of the language. Then I noticed that I got a lot of questions on my mail about Python bindings, and even some people, the one person who generated C-types bindings. But there has been a discussion on the GPIO Linux, on the Linux GPIO mailing list, that the C API uses this structure timestack. And this structure differs in layout, in memory layout and also the internal fields with a different size on 32 and 64-bit architectures. And I was not aware of that, but apparently there are distros that ship pre-compiled Python bytecode, even for like C-type bindings, which not byte by byte, not the C structure byte by byte. And this would be disastrous. So I want to implement Python bindings, but I will probably decide to go for C extensions and just craft them manually. And also I want them to be object-oriented and based on the C++ bindings. And the last thing that I plan on implementing is the GPIO daemon. So in the kernel, like for example in the device tree, you can specify GPIO hogs, so you can hog lines, you can drive them from boot time. And I thought that it would be nice to have something similar in the user space, so that you can reserve the lines with a daemon that starts early during the boot process, and then nobody can touch them from user space. And also, this daemon would be able to monitor lines and react to events by running external scripts or doing some other actions. Potentially, there's going to be bindings for other languages, because I got a message from a guy who also wrote Java bindings. I don't know why, thing. So this project is available at, it's hosted at kernel.org. It's available, the source is available from the kernel.org Git, and the releases can be found below. The project is available in Meta Open Embedded layer for Yocto and Gertrude. It's been packaged by people for Fedora, for Arch, and Debian Linux. And yeah, if you notice any bugs or want to contribute, please send patches to the Linux GPIO mailing list and add the GPIO prefix. And that's it. I'm actually quite fast, so we have plenty of time for questions. And, yeah. The tips for USB devices.
I'm just wondering if
if there are USB devices that support it, or it's a good question. So I worked with this. The question is whether I know about any USB devices that extend a regular GPIO line, like the GPIO chip. So I worked with this chip called CP2112, and it has a I2C controller on it over USB. I think it's also got some GPIOs, I'm not sure though. So this is the only one I work with. So I usually work on ARM, which has GPIOs already built in. So I don't know about that for
There's DigiSpark and DigiSpark Pro support.
So it's IntelliSpark what?
DigiSpark and DigiSpark Pro.
Okay, so I'll find the DigiSpark and DigiSpark Pro.
They're a couple of slightly older, tiny 18-based USB GPIO.
Do you know if they're supported in the kernel?
I'm not sure about that. They have some. I actually have questions.
Okay, cool.
So I'm one of those people who wants to be a user-based and wants to be good for other languages.
Okay.
So the system doesn't interface obviously has its limitations, but it also has its benefits as far as a very low prerequisite style of legal access to GPIO interface. Easily done from specifically using Golang. Ideally, you'd be able to not have any binary requirements, but you don't have to do the full compilation of C patterns. So, what do you think about that as far as
What is the question?
well, the Python supports mentioned using C-types.
No, I said that C-types can be quite dangerous. So the question is,
My name is Ron.
Okay.
The question is, what are you going to offer, as far as other language support that doesn't bring them all the same binary dependencies?
Okay, so the binary dependencies will be there because you're still going to go through the C library, right? It's just that, like what I said was that C types can be dangerous in this case because we're using C structures that differ in layouts and on different architectures. So C types may not be the best choice, and I decided to go with C extensions. So the C modules for Python. And as far as other languages go, so I know Python, I know C++, I don't know Golang, so I will never write. I don't think maybe it's something I will want to learn, but at that point I don't know it. So I will probably not be the one writing the bindings. If anyone's interested in writing bindings for this library in Golang, I will be glad to accept them and merge them.
Well, another example might be Node.js, where typically binary dependencies are going to be compiled in, but that has another set that are installation dependencies and another set of difficulties. So I guess it's just not requiring the compilation step on installation. It's one of the strengths of sysfs. I guess my question is, what do you do in your improved architecture to try to accommodate some of these problems?
Yeah, so you can always use, like in Node.js, I guess you could use the supplied user space tools. which are already compiled, and you can run them from your Node.js script. I don't know much about the potential use case for Node.js. I have no idea why Node.js would want to follow the
This is exactly your two examples. So,
Okay. So, yeah, this is my answer.
question is so abstract. I'm trying to figure out how you utilize this new technology, sort of touchless installation, when you file that. Rather than traditional binary dependencies, you also have traditional strings, but
Yeah, so as far as Node.js goes, I don't know. So this is my idea. Either use the tools and run them from your scripts, or write your own binding to the library and send them to me, and I will learn them. Yes, please. No, what? Yes and no. You can, multiple users can, so the question is, can there be more users for a single pin? Multiple users can read information about that pin, but once a single user requests it, another user cannot request it. Even from the kernel, actually, like, the kernel can no longer request that pin that's been granted to user space.
So if you have a monitoring GPIO, one running somewhere, it will be staying in the rest.
It will be what?
It will receive messages that other processes will get.
No. The question is if GPIO will receive messages about other processes wanting to. No?
If you have an application running, which is listening on the same pin as you are running GPIO 1.
You can't do it. No. Once it's requested, it's requested, and no other program can access it. There was another guy. Yes. Yes, this was the idea to multiplex access to yes, this was one of the ideas. So the daemon should have a client and will be able to multiplex. Actually, like I don't answer to your question. So yeah, now the idea that came to my mind is to have a daemon that offers like a socket or protobuf access to it, and multiplexes the access to GPIOs, and then we can deal with permissions and stuff like this. So this is something that's not implemented yet, and it's going to be maybe in the future. I do it in my free time, so it's not like I hold the time to spend on it.
How to compare speed with the systems
So it's I didn't do a lot of benchmarking, but there was this guy. Okay, so the question is how does it compare in speed with SysFS? I did not benchmark it as such, because the reasons for writing this interface were different. It's pretty good in that there was a person who submitted some benchmarking to the GPIO mailing list, and he actually fixed or improved the SysFS interface because just recently, because it was super slow because of the string parsing, which we don't do in this case. And even after these improvements, where we basically just check the specific bytes, it's still much slower. I don't know the number though. Which one? No. The question is if I test it with what is it? Real-time page? No. I don't know. So the question is if we can access a pin from SysFS and this new interface. No, because SysFS is another user of GPIO. So if you export a pin in SysFS, it's going to show up in GPIO info and the user is going to be called SysFS, and vice versa. If you export it from GPIO tools or this API, once you try to export it from SysFS, it's going to tell you, permission denied or busy, I think. Somewhere, I think I'm not the right, so. Yes. So there is this, you mean the simple API that I yeah. So there is a function, and you specify like callbacks, which are called, because the idea of the simple API is that to not have any resources that you need to manage. So it's like called contextless, and you just call a function, and then you pass it, you call a function is called like GPIO contextless monitor or something, I don't remember exactly, and you pass it two callbacks. One callback allows you, it's not mandatory, allows you to manipulate the polling, like to change the polling function, and then the second callback allows you to react to events.
But I need to use my own polling.
Yes, you can if you have your own script, like the question is you can use it in your own polling loop. So I do exactly that in this GPIO mon tool, because I use signal SD for signals, and I take this descriptor and I use this polling callback to just throw all the descriptors into a single poll system call, and then the events are taken by this another callback. So yeah, if you look at the GPIO mon source code of the tool, you're going to see how it's used in this way. Exactly. I think, yeah. Exactly. You can, both in this high-level API and low-level API, you have helpers that allow you to retrieve the descriptor and use it in your own polling functions. And this is exactly what is done. So basically, it's done first in this GPIO tool. It's already done using this high-level API, and then it's done again in the implementation of this high-level function, because the high-level function uses low-level function to implement and more straightforward interface. So if you look at the source code, you're going to find exactly the thing you're asking about. So sorry, the question was if you can use, you can retrieve the file descriptors from using the API, yes. Yes? Okay, we can use it now that I can't use it.
I think it is possible on later stage this project to evolve, for instance, if you have this tool, be able to provide some kind of feedback serial or SPI just for receiving or ESPRC, something like this.
I think you can use it now. Like you can use the library to implement big bundling of GPIOs because you can change the values fast enough and you can read all the events that come in. So yeah, I didn't try it, but I don't see why it's not possible. So the question is if we configure it as an input line, if we can still drive it. No, you cannot. Like this is how GPIO works. So if you configure it to be to run in input mode, you can read values. If you configure it to as a source of interrupt, you can still read the values. So it's the same as the input mode, but you can also wait, like get notifications about events. And then only if you configure it as output mode, you can drive it. It depends on how the line is. So the question is, if with the new API, it's possible to set the line and keep its value after it goes on the chip. So it depends on two things. So first, how your line is wired. If it's a floating thing, no problem with that. We're going to set it. It's going to set it. If it's cooled high or low, it's going to return to new values. But some work has been done in the GPIO subsystem to allow, like, to preserve values. And it's not advanced, but yeah, there's talk about having like preserving values lines, and but this is not done yet. And it could be another development to make it possible to use it. Right? It's not currently it's not done yet. Any more questions? Okay, so I think we're done. Thank you very much.